In this tutorial, we'll optimize the geometry of a molecule. This is an important operation in almost any molecular modeling situation. So let's get a molecule. We'll take aspirin again. This molecule is relatively planar. The two hydrogens are out of the plane symmetrically. And we'll use molecular mechanics for simplicity to optimize. We can use any of the procedures again, and setup determines which procedure we're going to use. When we do a geometry optimization, we have a choice of optimizers. Polak-Ribière is generally one of the better ones. We can optimize very tightly or relatively loosely at 0.1 kilocalories per mole. Let's leave it at that for the moment and just do an optimization. This optimization takes place fairly quickly. It relieves some of the strain that one has, but the structure that you get is still essentially planar apart from these two symmetrically opposed hydrogens. Now this is generally not correct, the final result, and that is because of the planar structure. It's something to watch out for when you're optimizing, and it's only the case for planar structures. Because it's planar, there are really no atoms here that have forces pushing them out of the plane. Everything is symmetric, and it's in the plane, and there are just no forces forcing anything out of the plane. In order to get a generic structure, we have to sort of start with a three-dimensional structure rather than just a two-dimensional planar structure. So if we select a side chain here and say rotate it around somehow out of the plane and then optimize, we're likely to get something that is lower in energy. And in this case we do, and this structure is not planar any longer. There's a different conformation of the correctly optimized structure. And in general, this is not really a problem because most molecules are really three-dimensional, that is x, y, and z coordinates rather than just x and y in a plane. But in general, if you have a complicated structure, there are maybe many conformations, and you have to be careful knowing which one is really the minimum, and it's probably appropriate to do a conformational analysis rather than just a simple optimization as we've done here. Having optimized, we basically have the same results that were available with a single point calculation, but at the optimized structure.